Hello, welcome to episode number 6 of this Device to Cloud episode. This one is going to be another theory episode. This one is going to be about security again. And in the last one, I talked about VPN and that being a technology to go and fuse two networks together, and which is really used in M2M mostly to go and create to achieve two goals. First of all, to create a secure channel into a device, and then to make that device addressable in one of two ways. Either, if you think about the private APN model that the mobile carriers have, is to go and make that device part of a network, map that into a network, and that you can then go and join from whatever your site is, where your system is, you go and join that network. Or the alternate way is to go and have a network of this sort, a private network that is around the systems you want to go and have the devices integrate with, and then the devices get joined into that network either outbound or inbound. But ultimately, there's a shared space between the devices and the backend services. And as I explained in the previous episode, that's not always desirable, as it really is trying to accomplish just the addressability of individual devices. And it's trying to accomplish a secure path, but then as a side effect kind of exposes all the systems that are sitting in those networks to each other. And then what you have to go and accomplish, if you don't want that, then you have to go and start segmenting those networks individually. You have to get effectively extra gear, extra software to achieve that kind of segmentation. And I already presented in the previous episodes 2, 3, and 4, a model that kind of avoids all that, and that is service-assisted connectivity, where VPN and network segmentations really don't play a role, but where a device will either directly or indirectly connect to a gateway through outbound connectivity going through a NAT. So it might go and do this using this path. The device itself goes and connects to a gateway device, and that gateway device then has a NAT and a firewall, and so it doesn't allow any traffic in, and it goes to a gateway. And really the connectivity, ultimately the application connectivity that exists, is happening through, let's say here's the control system, the system that wants to go and execute some data here or wants to collect some data here. That is happening by making the device addressable down here at the gateway level, where you send data to a queue with the name of the device, or to subscription with the name of the device, and the device ultimately pulls its commands from the system, which keeps it more secure. And I've told that story in the previous episodes. What I want to do today is I want to go and add some security concerns, and also see how we can need to go and address those additional concerns. So I'm going to use an example for this. I'm going to use one that I find fairly easy to comprehend. It's not necessarily one that is implemented like this in the real world, but I'm always trying to find examples which are kind of easy to follow. So I'm going to use a farm and an irrigation system, because that's something that most people can understand. And the farm, there's a humidity sensor. Let's assume that there's some kind of a pole, a thing you can go and stick into the ground. There's a sensor at the bottom, and then there's an antenna at the top, and that thing is wired up to some radio frequency network. And let's assume there's a huge farm that we want to go and sense. So we send data to a control system, and we send information about the ground being dry, like the desert, or a swamp. So there's some kind of a number that's being sensed on how humid it is. And then there's also obviously information in the control system, what's currently there, what the plants are, what they need in terms of humidity. And then the irrigation system is controlled based on those readings. And it's not only just turning on and off, but it's also directing the flow. If we're thinking about very huge farm systems, then you need to go and manage pumps that go and put the water into the right direction, manage capacity across the whole system. Probably also have different kind of things that are getting mixed into the water in addition, and that also needs to go and be managed. So we'll assume that there's some sensor readings here, and there's some control that's being executed on pumps, switches and on the irrigation system per se. So how important is it to make this secure? How important is it to not allow any interference with the system? How important is it to keep this private? Well, to keep it private is probably not so important because the humidity level on an individual field is something that you can probably sense with your finger if you care. And so that's not necessarily a business critical, mission critical information, but what is mission critical is the fact that the data that comes from the sensor is not falsified. And what you will need is you need to have some kind of assurance, and that's typically accomplished using a digital signature. You need to have some kind of assurance, or at best, a total assurance that that data here is actually what the sensor is observing. And the sensor itself can make sure that if the sensor is moved, it can shut itself off. It can take all kinds of measures against physical access. But as long as it hasn't been touched, it's there, has been turned on, has been activated, and it sits there, it will go and, let's assume, trusted, gives you the right data. What I can do, however, on the network level, if I'm able to intercept this and I want to go and sabotage this farm, is all I need to do is I need to go and change the values in here in transit. And I can do this by interfering with the radio frequency signal. I can go and try to interfere with the transport path here, or I can try to interfere with the transport path here. I can only assure that the data is not modified if I actually digitally sign that data end to end, and that needs to be happening on the application layer. And so what the effects would be, what would the effects be if I falsify that data? Well, if I make the data wrong, if I say the field is nice and nicely watered, but that's actually wrong, then I can go and dry the entire farm out. If I say, hey, it's really dry here, it's 10% or whatever, 5%, then I can go and turn the entire farm into swampland. So I can very effectively go and sabotage this entire farm. Now you'll say, who wants to do that? It all depends on who your enemies are. So one example that is very similar and that you can read up on Wikipedia and also in the news archives is certainly Stuxnet, which did more or less this. So the Iranian uranium enrichment program was attacked by governments, apparently, as we think we know. I mean everybody. And the key to success ultimately, after infiltrating the facility, which went through an infected USB stick, which was very clever, was to go and mask the readings that actually came from the devices, and to suggest to the control system, to the monitoring system, that the data was okay, and that they were all spinning kind of on their on the frequency that they were ought to be spinning on. So that data was falsified, while the control system bug was actually spinning them outside of their design envelope, and then ultimately ended up destroying them. So that is so Stuxnet did exactly this. They falsified the monitoring information. Of course, when you go and root the entire system, as was possible in that case, then all bets are off. But if you have a distributed system of this sort, where really the irrigation system pieces are connected by radio, and when I mean radio, I mean any kind of radio. It's either a private radio system, some kind of RF chip, but also a mobile carrier network, any kind of system that sits here and that you don't own, and that can be potentially, in some kind of way, infiltrated by third parties, that can be manipulated by third parties. That's something that you need to go and defend against. So that kind of digital signature is also important in end-to-end scenarios. It is important to make sure that the data is genuine, and for that we have mechanisms, we have algorithms to go and ensure that. Now, what you want to do here as a reaction to those readings, so you have those readings and those are observable things, what you do as a reaction to this might really be a secret. So you're executing some kind of command against your system, and maybe how you water your plants is really your secret of success on how you grow your whatever you grow. And so that might need the signature, and that might also need protection in the sense that that data is obscured using encryption. What is important, so you have signature and you have encryption, and so you have obviously keys that are being distributed. What's important is then is that the data is not only attributable, so signature also helps with attribution. You can say, well, this is device 102, and then you have some metadata in the system and it says, well, the location of device 102 is this, maybe it has GPS coordinates, whatever. And you can go and digitally sign this, so digital signature will allow attribution of where that sits and what the name of the device is. That will cover that with that key. But since that device is field deployed, what if that device gets stolen? And I as a malicious user, or someone, an attacker I should say, get my hands on it. In that case, I can now go and start forging data because I'm now in possession of a key if that key is shared. So what is required for that digital signature and also for the encryption is that every device, because it's field deployed, because I can go and take it, I can go and crack it open, I can get to the board and probably go and read all the electronic circuits out, it is required, or probably just go and read the flash memory out, it is important that this device has its own identity, and that this device actually has its own set of credentials, and that this device can go and be individually revoked because I cannot trust a shared key across devices that I have spread out around the world. So that requires that I have individual IDs, and that I have individual IDs really that I know inside of my system. There is a ID system, obviously, that exists in this network. So GSM, you have a SIM that gives you some kind of identity, and you have possibly WPA2 enterprise, where you can go and sign in from that device with its own identity here. But that covers the scope of this network. What you also need is to have a notion of end-to-end security. You really need to have an identity for that device in the scope of the entire solution that goes beyond the scope of an individual communication path, because your communication path will go through a variety of hops. And then ultimately, as you are in the control system, as you're writing data down, and as you're storing information, then you will often want to be able to deduce, you want to be able to attribute data even as that data is at rest. So any of the transport level security mechanisms are not necessarily going to help you. So that is to say that the digital signature piece is important if you want to make sure that the data is genuine. That encryption is often important as you are executing commands, and encryption and data protection is often more important than in the sensor data. But of course, if you have sensor data that's not as easily observable, if you have sensor data that comes out of machines, which is important, also could be trade secret related performance data of machines, you may want to go and protect that as well. And then you can't rely only on protection that happens on the individual paths, but you need to be able to also implement protection end-to-end throughout the system, and also have a notion of identity for those individual devices. That is all to say, we have a bit of work ahead of us to go and figure out whether and how we can go and protect data with those little devices, like the one that we have here. whether we could go and build a sensor, like let's say humidity sensor here, and make sure that the data is protected, and also how we can go and equip that kind of a device with an identity that we can go and then use in a control system to make sure that the data is actually valid and not purely rely on the magic that's given to us on the network infrastructure layer, but actually do that on the application layer inside that device. The key to that is a set of algorithms that we'll have to go and take a look at. We'll have to go and take a look certainly at signature algorithms. And in the Microsoft security lifecycle process that we are implementing inside of our developments that we're basing our development practices on, and you can go and read about this at microsoft.com/SDL, we have a set of algorithms that we have found to be useful, robust, and good, and that we're implementing in our system. And we actually have guidelines that are very tight about which algorithms we can and which algorithms we can't use in products. So one of the signature algorithm that we generally use here is SHA-2, SHA-2, and specifically we're probably going to take a look at the signatures with 256 bit length. The algorithm that we use generally for encryption is AES, for symmetric encryption, because payload encryption is something you do using symmetric mechanisms. And then if we need to go and exchange session keys on that particular path, then there's obviously the options of doing that using RSA, based on typically that's being used with certificates, which might be a bit of weight, adding a bit of weight, because a certificate requires a lot of processing that needs to be done, both cryptographic processing to evaluate the chain, to validate all the certificates on the path, or you can actually go and simplify this because of the way how the PKI infrastructure is built and what purpose that is built for. You can probably go and simplify this, and we're going to go and discuss this in the future episodes, and either limit the number of steps in certificate processing, or just do it without certificates altogether, and do key exchange using something like elliptic curve Diffie-Hellman, which is a particular way to go and exchange session keys to establish a secure link between two parties by exchanging keys for an encryption path, and then use that with one of the approved curve algorithms like P256 or P384 or P521. So this is a suite of algorithms which is inside of Microsoft approved to go and build with those things. If and only if you cannot solve this with pedestrian ways, which means take an existing protocol like TLS, like a tunneling protocol, an end-to-end protocol, and protect it this way. So there's a number of algorithms that we have available at our disposal, and in the coming episodes we'll take a look at the chances of implementing TLS on a platform that's as big as this. So I'm going to take a look at that, and also then see what the alternatives are, what we can actually do with a device of that size, just a few kilobytes of memory, to create a secure path to secure the data that comes out of here. Whether you really need end-to-end protection, so whether you really need to have let's say a digital signature from the device all the way back to your control system, that really depends on your system security requirements. Also depends on the architecture that you choose, and also the amount of investments you want to go and make here. The alternative to this is to go and not integrate deeply with those systems, but to take a trusted subsystem approach, and that's what we typically do in internet systems, so that the device talks to the gateway in this fashion, and that all the protection kind of happens at the gateway to device level, and that everything from the gateway down is then treated as a public subsystem. So you have both options, but what's important is that the data gets protected. So you can go and protect the data either through all the hops, through all the link layer hops on the route, so the radio and the wired network, or another upon the radio. So you have an end-to-end connection, end-to-end route that gets protected at the application layer. That is the important part, where you can establish the notion of identity, where you can go and do digital signature, where you can go and protect the data. And then ultimately you have two choices. One is to go and do end-to-end, pure, true end-to-end encryption, where really, and protection, where the data goes from the device to the control system. The control system does the evaluation of digital signatures, etc. Or you go and delegate that up to a gateway system. And we're going to go and take a look at both of those options as we go back into the code and investigate all those. Until then, thank you very much for tuning in again, and until episode number 7.